things. You need ideas. You need people to do the work. Can anybody tell me what the third thing is I need? Ideas, people, and
Money.
money. Right. Now, to get money for science, who pays? If I want to run an experiment, who do I go and ask for money? You have to go and ask governments, politicians, industry. You may be surprised that if I was to write to politicians and say, Obama here, next week, Modi is visiting Gujarat, yeah? Prime Minister's coming here. So Bala will meet him at the airport, right? And he'll say, dear Prime Minister, I want 300 billion rupees to find the origin of life. What is Modi going to say? Is he going to say, we have a vote, one, of course, don't know who you are, no problem. Aid, get the suitcase, give him the money. Or is he going to say, I've got a few other problems, water, famine, drought, telecommunications, health, I think I could spend the money better. So let's take a vote. Who thinks Bala's going to get 300 billion rupees on Tuesday? Who thinks he isn't? Oh, Bala, I thought there you were going to have a no. Right? You've got a don't know. Right? Will you tell them next week whether you get 300 billion, yeah? I'm afraid if I do that with my Prime Minister, I will be in category number 2. So, we need money. So the first thing you do to get money, a very good way of getting money for science, go and win a Nobel Prize. Because if you win a Nobel Prize, people give you money. The other thing is, if you're a Nobel Prize winner, people think you know something. So if you write a proposal and say, I'm a Nobel Prize winner and I want to design an experiment to understand how life began in the universe, you might get some money. And this is what happened to this person here called Howard Ullman. He won the Nobel Prize in chemistry. You get some money when you win the Nobel Prize, not 300 billion, but you get money. And then you got a student called Stanley Miller, who only died a few years ago, 2007, and they designed, next slide, an experiment. Next slide. They said, this is the early Earth, this is the ocean, water, heat the water up, mix it with methane, hydrogen and ammonia, the chemical ingredients they felt were the elements of the early Earth atmosphere. And then let's put some energy in to do chemistry. Chemists in the room, we need some energy, right? So we'll have discharge, lightning in the early atmosphere. And all the molecules of life can be made up here. We'll then freeze them out, or we'll liquefy them out down here, and the water which goes up nice and transparent will come down here, and it goes to a browny colour, which has a very scientific name, brown gunk. You can have yellow gunk, but it's called gunk. And you analyse it. Next slide. Carry on. So this is their original paper. This is what they thought would happen, and this is what they wanted to make, amino acids, like you find. That would be saying you make life this way. Next slide. This is an experiment we used to have at the Open University, which is a version of it. Water down here, there's the bulb for the water, there's the gas discharge up there, there's the condenser unit, and down here is where we collect the gunk. Next slide. So they ran the experiment for a week, they collected the liquid, they analysed it. This is in the 1950s and 60s, so you had things called chromatograms. Some of your seniors will probably remember these and may have used them. And they found 3 amino acids. They made 3 amino acids. So the conclusion was, yes, we can make the ingredients of life in the lab in a discharge. Next slide. The problem is, in all science, things move on. we now know that the early Earth didn't have those gas mixtures. There were volcanoes. If you've got volcanoes, you will get SO2. If you've got volcanoes and other gases, you will get CO2. If you put those into the glass bulb and run them, then the amount of amino acids you make is very small. But there's a bigger problem. We know approximately how much life there is on Earth. We know how many people there are. We know roughly how many animals are. We can estimate the number of plants. We know that 90% of life is bacteria and lives in the soil. We can calculate the amount of DNA on Earth, right? If you work out how long it would take to make all the ingredients to make those molecules, we are not here. And we will not be here until the sun burns us all to death at the end of its life. Alright. Now, you're being very quiet today, okay? So I hope the next answer is going to be a very positive yes, or I'm going to get really worried. Who believes we are here? Who thinks we're not here and don't exist? No one. I still saw some absentees there. So are there some robots in the room? So, the fact is, this cannot be what happened. Next slide. So, we have to have a way to get the molecules to make life on Earth and not make it here. One possibility is to bring it to Earth from space. Next slide. So let's think where it could have come from. It could have come from comets, it could have come from meteorites. We can collect some meteorites. Okay? I used to be able to this year be able to give a talk and say that we go out and collect meteorites. And meteorites fall to Earth, but there is no recorded incidence of somebody being killed by a meteorite. The only accident that we know about was in 1912 when a dog in Cairo was killed by a meteorite. But India has set a world first. You this year managed to have a meteorite that landed in India and killed somebody. Okay? Bala and a group of PRL went down and explored that site. And 1.5 hours ago, Bala gave me a very small piece of the material they think came down, and he wants me to take it away and analyse it and see, with the very sophisticated apparatus we have in the UK, of whether, if that is from a meteorite and what it's made of. Okay? Personally, I think that, my wife insists on me bringing back various presents, otherwise I'm dead. One of her insistence was bringing back her horoscope book for the year. The guy who was killed obviously had a really bad day, and I don't know what his horoscope said, but it was definitely a bad day to be travelling. If you take meteorites and you cut them open and you examine what's in them, you will find that amino acids are in there in huge quantities. So this evidence that life was brought to Earth, or the chemicals of life were brought to Earth, is possible. We've got evidence for it. Next slide. So the question then is, where do those molecules get made in space? How do they get made to come here? Next slide. Okay, so we now know about 140, perhaps up to 160 molecules have been found in space. Next slide. Click on, yeah, right. This is one of the molecules we found, formic acid. Can anybody tell me where you get formic acid from? What? Speak up. Formic acid. What animal gives formic acid? Ants. Squash an ant. Right? So clearly this tells me there are ants in space. Next one. Acetic acid in space. What's acetic acid? When do you use it? Vinegar. Fish and chips in England. Vinegar. We've got acetic acid in space. Next molecule. Glycolaldehyde. It's a sugar. We found sugar in space. Next slide. Next one. Glycine. Some people think with the most modern telescopes that we've detected a small amount of that first amino acid in space. Not confirmed yet. Next slide, next one. Benzene. Why benzene? It's a ring compound. Chemists, biologists, remember rings, need them. Nuclear bases, rings, 5, 6 members. Next one. But there are also molecules we find in space. Cyanopolynes, which are carbon, nitrogen, carbon, hydrogen chains, which we don't find on Earth. But you can see there's a huge, rich amount of molecules we've seen in space. We see them with radio telescopes in space. Some of them have been seen from Indian telescopes like Mount Abu radio telescopes here. Next slide. So we've got to work out how they get made in space. And now we have another problem. The chemists in the room will say, okay, I want to do chemistry. If I want a reaction to speed up, I heat it. Great. So if I go down in temperature, the chemical reaction will obviously slow down or stop. Space, where we make these things, are the dark regions of space. The dark regions of space, the temperature is 10 Kelvin. That's seemingly not good for chemistry. The second thing for chemistry, if I've got two molecules which are going to react in a chemical reaction, the one thing they definitely have to do is touch each other. They have to react, they have to interact. Space is very, very empty. Much more empty than we can make a best vacuum in our labs in the Earth. So we have a problem. It's too cold and the molecules never reach for each other, therefore there is no chemistry. But somehow we made all those molecules I showed you. So the evidence tells me I've made the chemistry, but our knowledge of chemistry in the 1970s and 1980s told us we can't. So it's a bit like being in the room. You know we're here, or most of you do. Some of you aren't sure you're here, but most of you know you're here. Most of us, we know the chemicals are made, but we don't know how. Next slide. So we worked out that the one thing that could happen in space is when you look into the sky, it looks dark. And you might say that's because it's empty. That's wrong. Many of those dark regions are full of dust. The dust comes from stars. Stars die, they explode, they throw out dust. That dust forms little clouds and hides the stars behind it. What does this dust look like? Well, if you go to a McDonald's in Europe, you'd be having your beef, can't have that here. You go and get your chicken burger or whatever, and you have a flame grilled Whopper or something in Burger King. That kind of blacky stuff on the top, what you might think is the carbonate soot, that's what these dust grains look like. Or sand. You've got lots of sand here. So that's what these dust grains are made of, and they're much smaller, they're 10 microns in size. We've collected some of those by spacecraft going out and sitting out in the solar system and collecting some of the dust. It's very cold there, so basically, if any molecules are made in space, when they hit the dust grain, they stick. And so gradually, over long, long time periods, millions or billions of years, because you've got a lot of time in space, you gradually form an ice layer on your dust. When that dust is irradiated by something, it might be a new star forming, and the light from that star, or it might be cosmic rays going through space. When it interacts with it, that's how we think triggers the chemistry. That's the theory. Okay? That's a theory. Now what we're going to do is see if it works. So we want to do some experiments. Next slide. So let's assume that what we want to do is make some dust grains in space and shine sunlight on them. So we need to make a star. Stars are made by nuclear reactions. Now unfortunately, politicians and government agencies don't like us doing experiments like that. Also, they're not very reproducible. So we can't make stars do that sort of thing in our labs. Next slide. What we have to do is find that gives the same light as a star, but maybe in a different way. And we do that with what we call a synchrotron, which is a light source. You have one in India, you have it at Cat Indoor. You might have heard it. Very imaginative names. The first one is called Indus 1, and the second one is called First one's called Indus 1, second one is called Indus 2, right? We use 2, one in Denmark, which is called Astrid 1, and is now called Astrid 2. In Europe, we often give our apparatus names. It's very common to give our apparatus female names. Why? Because experiments are temperamental and don't always do what you ask them to do. That's why we give them female names. We also use Taiwan. Barlow does these experiments. He does the experiments in PRL. He takes them to these machines, particularly in Taiwan. Next slide. So an apparatus looks something like this. You make the best vacuum you can. Remember, we're trying to make it like space. We make it as best we can. It's still not that good. It's very high vacuum, but not as good as real space. But it's good enough. We then make it very cold, and we freeze these chemicals and these ices onto a surface. Might be something like a dust grain, might be something else, to about 10 Kelvin. And then we irradiate them with this light from the synchrotron, or we shine electrons on them, or ions on it. And then we have to have a way to see what we've made, and we use spectroscopy. We use infrared spectroscopy. Every molecule has a unique fingerprint, right? You know, when I come to India, the first thing they make you do is do your fingerprints. That's because they are unique to me. Every molecule has the same spectrum, a spectrum that's unique to it. So if we want to find out what we make, we look at that spectrum. We can then identify the molecules we make. Next slide. So as I say, here in India, it's Barlow who's doing those experiments. He's pioneering those experiments here in Gujarat and PRL. This is him looking very smart. I think this was his PhD day, probably. And he's looking exactly these type of experiments here in India. Lots of experiments around the world, but it's also being done here. And if there's an opportunity to visit his laboratory at PRL on an open day, go. Great things to see. Next picture. So I can't do the experiment, I can't bring our Barlow's apparatus here. So instead we're going to do it as a thought experiment. And I'm going to give you 2 very simple molecules that we find in space everywhere. And that is water and carbon dioxide. So this is a spectrum. Don't worry about the shape. All you need to know is some of these lines tell me it's water, some of these lines tell me it's carbon dioxide. If I irradiate these species and make them mix together, can anybody in the room, chemists, tell me what I could make? Water, carbon dioxide, mix them together, fire lots of energy at them so they break up. What would they make? Sorry? Carbonic acid. Let's see if you're right. Okay, turn on the light. Now, okay, after 1 hour, we get the green light. New peaks. We weren't there before, right? That wasn't there before. Next. First thing we do is break up the carbon dioxide and we make carbon monoxide. We've now got an oxygen left over. Next one. That reacts with carbon dioxide to make CO3. CO3 then reacts with the water. Congratulations, we make carbonic acid. Very simple. I don't know if you give gold stars. You got a gold star. Right. Now, does this actually happen?